would be Ananya Passi from the Indian Institute of Science in Bangalore. And she will talk about the shape-sound associations, specifically, for example, why Kiki sounds spiky. I think it's a very interesting and curious topic. So Ananya, let's please talk about this.
Hello, am I audible?
Yes.
Okay. So, hello everyone. Today I'm here to talk about a very intriguing phenomena, that is the Kiki-Bouba effect. Now, what is it? You see two shapes on the screen. I would ask you, associate one of them with the name Kiki and the other of them as Bouba. So, what would you do? Most often, people associate the spiky shape on the right as Kiki and the rounded shape on the left as Bouba. But why is it so systematic? There are two competing hypotheses for it. According to the mouth shape hypothesis, when we say Kiki, our mouth forms an angular shape. And when we say Bouba, our mouth forms a rounded shape. Thus, our brain associates angular shapes to the word Kiki and rounded shapes to the word Bouba. The other hypothesis is the object sound hypothesis, which states that when angular objects fall, they produce a high-pitched sound. And when rounded objects fall, they produce a low-pitched sound. Thus, our brain associates spiky shapes to the high-pitched word Kiki and rounded shapes to the low-pitched word Bouba. But how do we test these hypotheses? We could use reversed unpronounceable words to test this. If the mouth shape hypothesis holds, then both Kiki and Bouba reversed words will not show the effect. However, if the object sound hypothesis holds, then they will show the effect, and most of the reversed Kiki words will be associated to spiky shapes, and the reversed Bouba words will be associated to rounded shapes. So the first experiment involved the validation of the stimuli. Here an image was shown to the subjects, and they were asked to associate one of the two names to it. These were the stimuli that we validated, and we saw that most of the spiky shapes were associated with Kiki-like words, and the rounded shapes were associated with Bouba-like words. And the results were consistent across subjects. The next experiment involved playing an audio recording and asking the participants to associate it to one of the two shapes. So these were the 6 different kinds of audio recordings that we showed.
Takiti.
Was this audible? Hello?
Yeah, we could hear it.
Okay. And so this was a pronounceable Kiki-like word, and this was its digitally reversed counterpart. Then we had environmental Kiki-like sounds. Then pronounceable Bouba-like words.
Lau.
Their digitally reversed counterparts.
Wal.
And environmental Bouba-like sounds. So, on playing these sounds, we saw that, of course, the Kiki-like and the Bouba-like words showed the Kiki-Bouba effect. However, the digitally reversed sounds also showed this effect, and so did the natural sounds. More interestingly, the responses to the pronounceable words and their digitally reversed counterparts was very correlated for both Bouba-like words and Kiki-like words. Interestingly, there was a nice correlation seen between the frequency of a word and the Kiki response that it elicited. High-pitched words were more associated with spiky shapes, and low-pitched words were more associated with rounded shapes. This was the case for all pronounceable words, reversed words, and also for natural sounds. So, in conclusion, we can say that the Kiki-Bouba effect is not limited to pronounceable words. And high frequency sounds are associated with spiky shapes, and low frequency sounds are associated with rounded shapes. Thank you.
Thanks, Ananya. It was a very interesting talk. I've never heard before of this effect, so it sounds quite interesting, this coupling between what we see and what we hear and what we see. And if I can start with question, one question would be, do you think that the reason for this association is in some kind of neural representation? Is there a hypothesis behind it?
I'm not very sure about what part of the brain is associated with this, but there are people believe that the prefrontal cortex is associated with the cross-modal associations.
Okay, that's interesting. Do you think that are there any similar effects that has this kind of shape sound coupling?
Yes, a lot of what we speak it has to do with the lip recording. McGurk effect is one of the examples. I could send you a link, and it's a very interesting optical illusion to see. So they're the same audio, but different lip recordings make us perceive the audio in different ways.
Wow. Oh, it sounds really interesting. Are any of the participants has any question, or the panelists have any curiosity on this talk? Let's see. So we have a question from Cleo Gergula. Very interesting, thank you. Do you hypothesize perhaps an evolutionary contribution resulting in this phenomenon of high-low frequency shape perception?
I think there is an evolutionary advantage of cross-modal associations. For example, when you hear a sound, it is evolutionarily beneficial if you can have an idea of what shape produces that sound. So I think cross-modal associations will have a benefit, but high pitch, low pitch, I'm not sure.
Okay, do you think that it can be basically as the brain has been evolving, that associating something spiky that can be dangerous with a high frequency sound may have caused this association? We are just speculating here, of course.
I'm not sure about danger, but I think it's useful in perceiving the identity of an object, right? I'm not sure of danger.
Yeah, and would it be also associated with the other senses? So here we are looking mainly at, we have a shape, is spiky, we see it, and we perceive the Kiki sound. Then would you expect that there is also an association, for example, with the touch?
Oh, I'm not sure, but I can tell you one thing. It is associated with other things. Like a similar experiment was done in which people were had to associate emotions with the shape, and they associated energy with the spiky shapes and peace with the rounded shapes. So that's another thing. I'm not sure about touch. Maybe there is an association with of pain with the spiky shapes and smoothness with the rounded shape. I don't know.
No, that's interesting. And would you like to tell us if you have already plans on extending this study, or what would be your next step?
Okay, so we have done one more experiment as a control. I can show that to you. We wanted to know if the mean frequency was the only thing that affected the Kiki-Bouba-ness. So what we did was we created sinusoids of the same mean frequency as the words. Like Bouba, the word, I computed a sinusoid of that main frequency. And we asked people to associate it with the spiky shapes and the rounded shapes. And here also we saw that there was an association. So tones of the Kiki words had a like were more associated with spiky shapes than the rounded shapes. And again, but there wasn't much as a correlation as the pronounceable and reversed words like this. And it was a weaker correlation. So this is one thing that we did. Another thing that we want to do is we want to make a model, a sound shape predictive model that would be made on like trained on object images and the sounds they produce. And then we want to input object like Kiki-Bouba images into that object and see if they produce sounds that are similar to the words Kiki and the word Bouba. This is one thing that.
Yeah, that's very interesting. And if I can ask you a last question, and of course, if the participants or the panelists have other ones, we can also go with them. So you showed in the bar plot that the actual words, Kiki and Bouba, yes, basically they are very, very different. And then when instead you go to the tones, so the natural sounds that resemble them, they are still different, but they are kind of get closer. Do you think that instead of using real sounds, if you used just basically a sound based on a sinusoid of different frequencies, so basically a vibration, something like that, that it's not as complex as a real world sound, do you think that you would have something as the Bouba Kiki difference, so such a striking difference?
We did this. So the tones that the thing that you're speaking about, simple sinusoids, we just call them tones. So the tones did show a difference in the responses. Like the tones correspond, like high pitched tones were more associated with the spiky shapes, and low pitched tones were more associated with the rounded shapes. But the effect was not as pronounced as that of the complex words that we say like Kiki and Bouba.
Okay, then I guess that we rely on not just the main frequencies, but also on the harmonics that we produce with the words. Thanks again, Ananya. It was a very interesting talk.
Thank you.
And we can move on to our third talk from